Good morning, everyone. My name is Ron Wainberg. I'm Technical Director at MRA Consulting Group. We are a waste management consultancy based in Sydney, operating Australia-wide, and our speciality is waste and all things associated with it. That brings in the circular economy, because the two are very they're not the same, but they are linked very closely. I think circular economy, from the waste perspective, the circular economy is misunderstood. People in waste tend to think of circular economy as recycling, but it's much, much more than recycling. It really encompasses designing out waste. When that isn't possible and when waste is generated, that's when we come in. How do you deal with the stuff? And you've got to have the whole spectrum of activities, from collection through to processing, disposal, or whatever. Right. So where does that fit in with the circular economy? It's a really good question. And I hope that this morning's session can explore that and get a few ideas going. We've got three speakers this morning. Myself, I will be talking about where the circular economy and energy from waste fit together. Then we've got Roni Habbal, who will be talking to us about renewable hydrogen from biogas. And Grzegorz Lisak, it's a very difficult name for me to pronounce. I'm terribly sorry. I'll call you Greg for the sake of simplicity. Greg will be talking about gasification and where that fits in with energy recovery and waste and the circular economy. So after that, we'll have a question and answer session, and hopefully we can get a few ideas going and get some thought processes in place. So let me share my screen. Just a minute, I've got to set this up. Circular EFW and the circular economy. What I'm going to talk about is, where is EFW and what role can it play in New South Wales, and how does it reconcile with the circular economy? Generally, if we take the traditional view of the world from a waste perspective, we've always talked about the waste management hierarchy. That lists what we should be doing with our wastes, from the most to the least preferable. At the top of it, at the top of the tree, we should be avoiding the stuff that goes through reusing it, recycling it, recovering energy, which is where this talk is about, treating the waste and disposing of the waste as the least preferable option. So preference goes up, but unfortunately ease goes down. The easiest thing that one can do with waste is find a big hole in the ground and throw it in and bury it. That's led to the problems that we're experiencing today, because we have a lack of resources are slowly being depleted. It's very difficult to find a place, a hole in the ground to put the stuff in. And of course, you have long-term intergenerational poor environmental impacts as a result. So this is the aim that everyone's had. The New South Wales EPA has adopted this, as have other EPAs in the country, but its implementation has been mixed and tends to be more focused down the bottom. So along comes the circular economy. This diagram, I'm sure you're all familiar with, is from the Ellen MacArthur Foundation, and it really focuses on the top of the tree and sees waste as something that we design out of our economy. Materials get reused, they get shared, the items are repaired, and it all goes round and round in the circle, with a very, very small amount of material dropping out the bottom into disposal, and that would be minimised. So if you look at it, oh dear, sorry. If you look at it all together, that's how the two, if you like, fit together. The circular economy really is a better way of expressing the top part of the hierarchy. Now, if stuff is going to flow through to the bottom part of the hierarchy, energy recovery, treatment, and disposal, the amount of material that's flowing down there is going to really depend on how efficient the circulation is up the top. If it's very efficient, meaning if we get very, very circular, indeed, if we achieve full circularity, there'll be very little, if anything, flowing down the bottom. But I put it to you that that will take time. That'll take a long time, because we're talking about a fundamental change in the way the entire economy is structured. You've got the simple fact that industry seeks to sell more goods. Industry's production is dependent upon people buying a new thing. You've got fashion coming in, and there's a severe cultural change that's going to be necessary in society to achieve full circularity. I'm not saying it won't be achieved. I'm saying it will take a long time. And meanwhile, we've got residues that we have to deal with. And those residues are not going to wait for us. We don't want them to pile up. And I personally, I think most people would agree, we don't necessarily want them to go into a landfill. So how do we stop that? Well, what are the options? I've shown there I've blown up, if you like, the bottom of the tree. I've got the Ellen MacArthur butterfly up the top. That's not meant to demean, it's just for the sake of space. If waste is being generated, the first thing we have to ask ourselves is, can we separate the materials? If we can't separate the materials, we're going to go this way to the right. We're left with a pile of stuff that there's really not much we can do with. At present, the only approaches I'm aware of for dealing with mixed general waste is either through thermal treatment, combustion, gasification, pyrolysis maybe, RDF, or sending it off to landfill. People have tried anaerobically digesting this material. Anaerobic digestion of mixed municipal or commercial waste has not proven to be very successful. For mechanical reasons, the digesters tend to clag up with a whole lot of materials that weren't taken out. If you can separate the materials still, then there are other options available. In New South Wales, we used to have what we called MWOO, mixed waste organic outputs. This was the organic material that was left in mixed waste. It was processed, composted, and applied to land under certain circumstances. The EPA has put a ban on that. It cannot be done anymore, and so it is no longer an option. Meaning if we do separate the material, really the only way we can go, if we don't go through to is chemical recycling or anaerobic, or going down to anaerobic digestion with the residuals going to the left, to the right rather, and being disposed of. That's a biological treatment option. But EFW's role is not very well understood. If you don't separate out the wastes, there's a limit to what you can do with the material. As I said, it'll either have to go to landfill or it's got to be burnt to recover the energy value. But there's a lot of well-intentioned, misguided opposition to it. What I've reproduced there is a resolution from the New South Wales Local Government Association conference from March this year, where they adopted a motion that said that local government New South Wales considers burning energy an outdated technology and encourages diversion rather than incineration. Leaving aside the grammatical question of what does burning energy mean, I think they mean burning waste to recover energy. I think that position is very well intentioned, but it's unfortunately misguided. It sees energy from waste as competing with resource recovery, whereas in fact it does not. Energy from waste is what you do with materials once you've recovered what you can and you're left with the residuals. If we look globally at what is happening in countries that do have thermal treatment of residual waste, they get maximum landfill diversion. You probably can't read the detail in that slide, but on the left-hand side, countries like Sweden, Germany, Denmark recover a lot of material, a lot of energy from their residual waste. They have high landfill diversion, and they have high resource recovery as well. Moving over to the right, not so much the case. And Australia is unfortunately well over to the right. The Sydney region's landfill capacity is depleting, and it's depleting quite quickly. New South Wales government recently prepared a paper called, strategy, New South Wales Waste and Materials Strategy, Guide for Future Infrastructure Needs, was released June last year. They note that Sydney's putrescible landfills will reach capacity around 2036 and the non-putrescible landfills around 2028. What are we going to do with this waste? Because we're not going to achieve circularity. We're certainly not going to achieve 100% circularity, but progress towards it, significant circularity is not going to happen in the next 5-6 years. Developing a new landfill site is going to be a real challenge. You can't do it, I don't believe, in Sydney. I don't believe there'll be any more large-scale waste infrastructure in the Sydney Basin, which means there's going to have to be long-haul transport, implying extra cost. And of course, the question is, where to? Developing waste infrastructure, landfills, or energy from waste facilities is a long-term process. We have approximately 10 years to go, and there'll be nothing new until 2032 if we were to start tomorrow. I should say if we were to start yesterday. I think if we're not careful, there's a crisis coming. There's lots of holes around, but let's get the social license to use them or to build energy recovery facilities before we get ahead of ourselves. So where should energy from waste apply? We need clarity of what's being dealt with. And this comes back to the local government resolution I mentioned earlier. Typically, households in Australia have up to 4 bins: a red, a yellow, a green, and sometimes a blue. Education of the community about what material goes into what bin is vital, because energy from waste only applies to the red bin. The green bin goes to compost. The yellow bin and the blue one, if you've got one, goes to recycling. It's the red one which is destined for disposal, landfill or energy from waste. We have to get society to minimise the red bin contents. We need the right collection infrastructure, the right processing infrastructure, and of course, with the material that is reclaimed, you've got to have a market for it. The recent experience with RedCycle and their collapse trying to reprocess plastic bags is a case in point. The market wasn't there. The whole thing fell over, unfortunately. Energy from waste helps to maximise the resource value of the residual by getting the energy out rather than just putting it in a hole in the ground. Now, energy from waste can take many forms. It isn't just incineration, and we'll talk about that a little bit more in a minute. I want to mention disaster waste. It never seems to be considered, and it's probably going to increase. We've seen a lot of it in New South Wales in the last, during this year. Unfortunately, you can't predict it. So it's very, very hard to build infrastructure which would cope with this stuff because it arrives in a sort of ad hoc basis. If you get a bad fire, if you get a bad flood, you're going to have disaster waste. But there's no way of really predicting long-term the amount of waste that will be produced that would make one or more processing plants or whatever for this material, or recovery plants for this material, financially bankable. What is the answer? Unfortunately, it's going to be disposal. Remember, there's a lot of it coming in one hit. Now, talking about the different types of energy from waste facilities, we're going to hear about some innovative stuff from other speakers, looking at gasification and hydrogen and so forth. But there are many pathways. Combustion is the classic way of doing it. There's over 2,000 incinerators that have been built around the world. These are omnivorous. They will take all the waste that you can throw at them. The stuff that can be burnt will be burnt. Other stuff goes through to the ash. You can get metal recovery from the ash, and the ash can be used in aggregates. Unfortunately, this has a very bad reputation in Australia. There are a couple of plants being built in Perth right now, and there are 4 plants in Melbourne that are at various stages of development. There are none in New South Wales, though there's a couple of projects that are starting to raise their head. The one at Parkes and the Veolia proposal at the Woodlawn mine. But energy from waste combustion has an extremely bad reputation. There's a lot of community opposition and a lot of misinformation. And I find that to be a pity. The picture there on the left is actually a snapshot of a website put up by a community group in Sydney. They were opposed to the proposed energy recovery plant at Botany, which was going to burn commercial waste and paper mill wastes. And that is the picture that you can see that was put on the website to garner community support and get the thing banned, and they were successful. My point is that that photograph is not true. It's depicting the energy from waste as something that it just plain isn't. It doesn't have that type of output coming out of it. It is not that dirty. I don't know what that photograph is. It looks like a steel mill somewhere, and it was taken 100 years ago. We don't do that sort of thing these days, certainly not from energy from waste plants. Unfortunate, but that's the sort of thing that's floating around. That's what a modern energy from waste facility looks like. That's the Copenhagen incinerator. It doesn't bellow volumes of black smoke. It isn't an environmental problem. So what's the take-home message from all of this? I think Sydney's landfill capacity is nearly depleted. New capacity in the Sydney basin is, I think, very unlikely. It might happen, but I've got my doubts. If we can circularise the economy, that's positive. That really is a step in the right direction. Get rid of the culture of maintenance by replacement. Let's have maintenance by repair. Less waste would require disposal, but it'll take time to change the functioning of the economy. Meanwhile, we're going to have increasing quantities of disaster waste, and the waste that we are generating anyway is going to keep coming in the door. We have to manage it. Without a circular economy, large regional waste management facilities will be necessary, and we should start to plan their development now. And as part of that, there's got to be consultation with local communities. That really is critical, coming back to what I said earlier about the misinformation that's out there about what these facilities are like. Energy from waste, in the absence of a fully circular economy, energy from waste is an essential part of an integrated waste management system. I want to stress that. It's not the waste management system, it's part of an integrated waste management system. If you remember the slide I had earlier, we're dealing with the stuff that falls out of the butterfly, the stuff that cannot be recovered, but still has calorific value. Long term, we're going to have waste transport infrastructure in the Sydney basin to move the materials to where they can be processed. And in all of this, there's really a critical role for government to play. Negative community perceptions about energy from waste must be challenged with facts, and that's something for government to do. Western Australia and Victoria experience, I hope, will help when the community get a chance to see that these facilities are not monsters. But can New South Wales wait while those are built? Because our landfills are filling up and we've got to start to do something. So that's basically my little pitch. I don't want to go on any longer. Let me close down. Okay, I would now like to introduce our next speaker, Roni Habbal, who is going to talk to us about renewable hydrogen from biogas. Roni is the Chief Commercial Officer at ScimTek Hydrogen, an Australian-based cleantech firm that's revolutionising the use of waste resources to harness them to produce low-cost and low-carbon hydrogen fuel. Roni's worked with Suez previously, both in Australia and internationally, looking at low carbon solutions and energy from waste. And prior to that, he worked overseas with Schneider Electric. Roni, over to you. Please go for your life.
Thanks, Ron. Can you hear me well?
Yes.
Okay. Hello, everyone. Nice to meet you. It's really a pleasure to be speaking today about energy recovery through an alternative and innovative pathway, which is converting biogas into renewable hydrogen. As Ron was saying, there's a lot of focus on large-scale thermal processing facilities in Australia, but apparently there's also an opportunity to recover energy from different feedstocks that is not fully addressed today. So I'm going to be talking about the opportunity for Australia to harness its bioresources, specifically organic waste and agricultural residues, to actually produce renewable hydrogen and accelerate that transition towards a zero carbon future. Before I go deep into that, just wanted to say that today there's huge quantities of organic waste, more than 10 million tons of organic waste ending up in landfills. There's an estimation that there's around 1,200 landfill facilities. Most of them are licensed, many of them are not. And all of those landfill facilities are producing significant amounts of methane emissions. We all heard about Australia signing up to the Global Methane Pledge 2 weeks ago, and the commitment to reduce methane emissions by 30% by 2030. Unfortunately, despite all the efforts that the waste industry is putting on capturing waste methane from landfills, we still see huge amounts of methane being released into the atmospheres in the form of fugitive emissions or lack of efficiencies, or simply because the landfill gas is not recovered properly. There is actually 13 million tons of CO2 equivalent emissions being released every year still, despite all these efforts. So what can we do about this? How can we address this methane challenge at the national level? As we mentioned, most of the organic waste today, if it's not going to composting, if it's not being source separated, it's ending up in landfills. And this is creating a lot of biogas. There's other types of organic feedstock, such as agricultural waste, manure from animals, and crop residues that goes to different facilities, such as anaerobic digestion facilities in regional areas. In many cases, those types of residues are not even processed, and they are decomposing on the land, producing a lot of methane emissions. There's also a number of anaerobic digestion facilities in urban areas trying to process what's available from urban organic waste, such as industrial waste or liquid waste, grease trap, and also wastewater treatment facilities trying to recover biogas from sludge. From that biogas, there's a significant portion that's not being recovered today, and there's a significant portion that's being released into the atmosphere. So we want to develop a technology and a value chain that can actually ensure all of that biogas is recovered and all of that methane coming from biogas is being addressed. Now, it's probably worth mentioning that biogas is a mixture between methane and also carbon dioxide, as well as other gases like H2S and nitrogen. So in terms of the current situation with the biogas industry, we noticed that if we look at biogas systems in the landfill sector, around 50% of that biogas is flared. So it is being converted into carbon dioxide, and we are losing that energy value from that biogas. Only 4% of biogas at the national level is being used to produce electricity. And that is related to a number of reasons, because many of those sites do not have a connection to the grid. There's insufficient infrastructure on the site, or also because there's challenges in actually selling electricity to the grid and finding energy off-takers for it. With solar and wind becoming cheaper and cheaper, producing electricity from biogas as a business model is becoming more challenging for many proponents in this industry. So they are also looking at alternative solutions to utilize that biogas. We also see that to invest in a biogas conversion asset, this is usually associated with high investment cost. And even though there is some support mechanisms like the Renewable Energy Target and the Emission Reduction Fund mechanism, it's not enough for us to have a biogas industry at scale in Australia. We still need to see more government policy in that space, more certifications for biogas-derived products for this industry to grow and for us to be able to make the most value of the biogas resources. So what we are trying to develop is also an alternative value chain for biogas. We believe that if we upgrade biogas into biomethane, we can unlock further value for biogas. Now, once we upgrade that biogas into biomethane and we separate that carbon dioxide out of the biogas, we will end up with a biogenic methane feedstock that we can use in many ways. Many proponents are looking at injecting that biomethane into the grid, so to offset and to displace natural gas in heating applications or in cooking and home applications. But there's also an alternative pathway that we think has a high merit and can really support Australia with its decarbonization journey. If this biomethane from biogas is actually reformed into hydrogen using existing technologies, we can produce green hydrogen fuel, renewable hydrogen from biomethane. And as we know, there's a lot of focus on how we can use this hydrogen in different hard-to-abate sectors, such as heavy transport, on-site heavy equipment, and also in power generation. We believe that converting biogas into hydrogen through this biomethane reforming process will unlock this value for biogas. And for the hydrogen product itself, instead of selling it to the market at wide scale, the idea is that the hydrogen will be used on-site to power heavy equipment like compactors, heavy trucks, and other heavy-duty machinery, and be able to create a circular economy value chain on-site where the local gas is used to power the local fleets. There's also an opportunity to dispense this renewable hydrogen into waste collection fleets and into waste transfer fleets. There is often a lot of back-to-base operations happening between the landfill sites and waste transfer stations where the waste is coming from. So there is an opportunity to use that landfill gas, convert it into hydrogen through reforming, and then use that hydrogen to power those fleets. By doing so, we can offset a significant amount of diesel. Actually, we did a bit of modeling on this, and we realized that if we converted all the biogas potential in Australia into renewable hydrogen using reforming, we can create 1.14 million tons of hydrogen every year, which is a huge amount. And this is enough to displace around 40 to 45% of diesel consumption in the transport sector, mostly in heavy trucks. And if we do that, then we can achieve around 50 million tons of CO2 equivalent reduction per day. So this, if we achieve actually that target, not only are we addressing the methane challenge that we have talked about at the beginning, which is coming from landfills and organic waste decomposition, we're also supporting the decarbonization of other sectors. So we really believe that this pathway, not only does it offer an innovation to the biogas industry and to the waste industry, it also offers a pathway to replace fossil fuels in hard-to-abate sectors and assist Australia in its transition to net zero. Thank you.
Thanks very much. Very good, Ronnie. If you stop sharing the screen, we will move on, take questions at the end. Our next speaker is Greg Lisak, Assistant Professor from the School of Civil and Environmental Engineering at Nanyang Technological University in Singapore. He's going to talk about, is there a place for EFW in the circular economy? And he's going to look specifically at gasification. Greg was recently appointed to the External Advisory Panel for Environmental Sustainability by the Singapore Ministry for Defence. He's a Director, Residues and Resource Reclamation Centre, Nanyang Environment and Water Institute, and a co-founder of a company called Nanomatics Private Limited, providing solutions to waste plastic and recovery resources from plastic waste. He's had various academic appointments in Sweden and Australia. I'll now pass over to Greg. Take it away.
Thank you, Ron. Can you hear me well?
Yes.
Perfect. So welcome, everyone. Good morning. First of all, thank you for inviting me to give this talk. It is a pleasure to be here, and I understand how important this subject in Australia is and how much we have to actually straighten the information out in order to give that better perspective, or actually a true perspective of what waste to energy is. So today I'm going to talk about the concept of waste to energy as we know it, and I will present it in a way that there is not only energy that we can recover from waste, but there is also a lot of resources that one can get out of the waste so that they will feed again back to that circular economy concept. And for that reason, I will present here a different technology, thermal technology, which is a gasification, more specifically high temperature slugging gasification for generation of electricity, as well as utilization of byproducts, which no longer have to be landfilled, but can be directly utilized with a specific purpose of using them in construction industry. And for that reason, I will present you a work on so-called new sand. It's a brand name in Singapore for that ash that comes out of incineration and gasification processes that can replace vital components of concrete, so that actually decarbonize concrete making as well as the concrete-based industry, the civil engineering part. Singapore is a waste-to-energy country. We have 4 waste-to-energy plants, and there are a few more being considered or built as I speak. We address all our general type of waste using incineration, because this is the only way and the simplest way to lower the volume of the waste that finally will be disposed to the landfill, but also we recover the energy. I think quite much of the information which Ron shared may overlap, so I apologize for that, or I try to skip it, but for sure it should help you understand what I'm trying to convey. So what sort of waste we are addressing? We work on municipal solid waste and also sludge that comes from the wastewater treatment plants. So this type of waste, which is very difficult to be recycled, it's something that it's intermingled, it's dirty, nobody wants to touch it. The recyclers will not approach it because cleaning it up would require a lot of energy and resources to be spent in order to get some valuable materials out. So ultimately, for most of this type of waste, the thermal treatment is the way to go. You don't want to dispose this to the landfill because you start losing control of what these materials may release back to the environment. And we know that this, if the waste contains a lot of organics, and this is a composition of waste in Singapore containing a lot of food residues, we know that this type of waste will generate a lot of methane. And that is much worse a greenhouse gas than CO2. So why to contribute additionally to greenhouse effect through incorrect practices in waste management? So typically in Singapore, we would incinerate our waste, and whatever comes out as byproduct, except of energy that is fed back to the electrical grid, is a bottom and fly ash. And that ash currently in Singapore is being sent to only landfill that we have. It's an offshore landfill, you can see here island, and it's quite filled already. So we expect it to be filled by 2035. There is no direct plan of what to do next. So actually we are currently really focusing on either redirecting this type of waste and trying to find applications for it, which mostly would be in the construction industry as that so-called new sand. And the other option is even to excavate the landfill materials for resource recovery. So we are talking about resource mining. And we have to do it because there is no much space left in Singapore. And obviously you don't want to build another island. The sea resources around Singapore Island are also very much valuable. So having that sort of waste management practices also already established in Singapore, now we are on the next stage. What to do in order to maybe apply a different type of technology that would complement incineration and expand that sort of energy and resource recovery. And this can be offered by gasification, high temperature slugging gasification. NTU is the only unit in Singapore and worldwide that would have a demonstration plant, waste to energy demonstration plant of this technology. So NTU coupled with a National Environmental Agency in order to build and test this technology within Singapore to see how well it fits into waste management structures. So we need to test if this type of waste that we generate in Singapore is suitable for this type of technology, how it can be beneficial for incineration, since the bottom ash that is generated in the incineration can also be fed to the gasifier in order to treat the bottom ash for more stable residues. So what type of residues I'm talking about? The byproduct of this technology, it's not in bottom ash as in incineration, but it is a slag. And that slag is relatively similar to sand. And it is very stable material. So for that reason, without any further treatment, can be applied in the construction industry for incorporation instead of sand into concrete design. And already at this point, I can share with you, we do have a high confidence in this type of material in terms of environmental performance. And even the plaza that is around environmental agency building is constructed using that slag. This is show you how confident our agency is in environmental suitability of this material to be reverted back to for some applications. Also, this facility has been constructed in Singapore by university to obviously increase the sustainability efforts of the university and Singapore in general in resource recovery and energy recovery. Also, it does provide an unbiased evaluation of this type of technology, so that information that comes out of it would not come from industrial side, but would be validated by third party, which is the university. So we do have a strong drive to be leaders in sustainability. And for that reason, we operate, although university typically does not, but we operate this sort of relatively big facility that treats 11.5 tons of municipal solid waste per day. This technology, as I mentioned, is high temperature slagging gasification. It can accept very different type of waste, municipal solid waste, sewage sludge, incineration bottom ash, any sort of bioresidues, even medical waste, and some radioactive waste if needed. So in Singapore, we generated quite a lot of waste. This is statistics from 2021. And this waste would come either from domestic or non-domestic sources. We are quite good at recycling waste from non-domestic sources, meaning industrial waste, because this type of waste is relatively clean. But domestic resources would have only 13% being recycled because of that very difficult nature of the waste, which are dirty and hard to clean and hard to recover. So ultimately, as you see it, there would be a lot of waste beyond recycling, what we can recycle, that finally has to be treated, what also Ron mentioned. This is a cross-section of the process itself. The key parameter here in the process would be the high temperature gasifier, where we drop the waste together with auxiliary fuel and slagging component to gasify the waste, meaning that to produce a syngas that consists of carbon monoxide and hydrogen that later on would be combusted in secondary combustion chamber to generate heat, which would be used for power generation. And the other half of the process is basically a cleanup of the gas. So there is a stringent process for cleaning any sort of toxic components and things that you don't want to be released to the environment. So whatever comes out of the stack meets the requirements for the release of gases that is regulated by each country. This process that what we apply was built in order to conduct R&D work. So we identify multiple places where we can plug and play, and we invite industry as well as universities to come and join us and look into test bedding different technologies around waste to energy. Then I move on to circular economy, and I think Ron did a great job describing of what we have to do in order to be really circular. I just want to mention that basically without final treatment of waste, which also would be smart, that would be directed towards further resource recovery, you really cannot talk about net zero. You cannot really talk about being fully circular, because you're gonna always generate residues. No matter what you do in that circular economy concept, you will have sideways of different waste streams, obviously smaller than currently what we have, but they still gonna exist, and you don't want those waste to be sent to the landfill. You want them to be treated for environmental benefits, but also for energy recovery, and ultimately also for resource recovery. So when you have that cycle, when you design, use eco-friendly materials. When, as a consumers, we have to be thinking of what we are buying, how long we're gonna use it, are those eco-friendly materials, and so on. So actually, we as a consumers, we are part of the circular economy design. So there is a power in our hands, because we drive of what is being designed and what is being built and how much of it is being built, right? So let's not forget about that as well. Then we have the collection and recycling of the materials that come out of post-consumer use. So we have to be smart about it. We have blue bins. I understand from Ron that you have different type of bins where you collect your recyclates. But this system also has to be improved for better resource recovery. And finally, you are able to revert back the materials to that circular economy design. But again, you're gonna generate waste. So let's not forget about that. This circular economy without waste is simply utopia. So we need technologies which are end of life for anything that is no longer possible to be reverted back, to be treated. And this is where we come in with our gasification technology, which is a next generation from incineration in terms of energy and resource recovery. So I'm going to present you some work that we did on treating sewage sludge, another type of waste that is horrible to be treated. So currently in Singapore, we generate a lot of sludge. And that sludge, dewatered and dried, would be simply incinerated, but without energy recovery. Because it does have a high moisture content, you actually have to supply a fuel in order to burn it. So that sort of incinerator, which is just for final waste treatment, is not an optimal option. What we want in Singapore is to be able to convert this waste to useful resources and energy. Additionally, we generate in Singapore waterworks sludge, which has a high inorganic content, and that one would be going directly to our landfill, and we want to avoid it. So the technology that we propose, high temperature slugging gasification, can address all this type of waste and generate useful byproduct. So we are now in the process of rethinking sludge management in Singapore. So I'm not sure if you are familiar with the concept of new water in Singapore, But what we are currently doing, we are generating a new sand. So that's another thing. Whenever you develop a material that possibly is of waste origin, you should also think about perception of it. And in Singapore, we are branding things. We are giving them names that perhaps they take them away from where they come from. So hearing new sand is easier than talking about post-waste treatment materials, for example. Here are the type of sludges that we used. Together with the sludge, we also tested different incineration ashes that come from the current incineration processes of that sludge. And we designed the study in order to mix municipal solid waste with different amounts of sludge and different types of sludge or their mixes. We designed them in order to have low and high loading rates to push the system to see how far we can go with the system and operate in stable and environmentally friendly conditions. So the process would look like this, that we feed municipal solid waste at different ratios with the sludge and their ashes into the gasifier. As a gasification process would continue, we generate metals and the slag, or that new sand, as I call it, that both products can be reused for different purposes. They are commercially viable products, we can sell them, while the gas that is being generated in this process would go into generation of electricity, and then after the treatment of the post-combustion gas, then we can release the gas back to the atmosphere that is in compliance with our environmental agency regulations. So gasification offers you another function. Aside of generating these byproducts, if you would break the process in the middle, you generate the syngas, and without combusting it, you can recover the syngas and drive chemical synthesis. So what we believe the next step of development waste to energy in this type of processes would be to drive waste to fuels and waste to chemicals domains after the recovery of syngas from the treatment. Then here I just present you a test that we conducted. All are standard-based tests. I know the slide is a bit boring, but I show it to you only to let you know that whatever we generate, we really have to comply with a number of standards in order to identify those materials and processes suitable for, in terms of environmental applications, in terms of use of the material in final applications. So it's not that simple to simply generate the materials and apply them elsewhere. You have to comply with number of standards so that the process can be deemed environmentally suitable. So here are environmental parameters and some geotechnical parameters for the slag, for the new sand, to identify its suitability as a replacement of the sand. Here is presented a table, or actually two tables of different leaching protocols. And you can see the results of one type of mix that we treated and resulting from that slag. And the metals that we identify in slag were compared to EU criteria for inert materials. And we basically meet all of them. So according to EU regulations, our material is safe for reuse. Then we compare ourselves to National Environment Agency of Singapore reference values, which are more stringent than EU criteria. And then we are at the border with a few elements that are marked in red. Nonetheless, NEA reference values are not standard. Those values are set to be more stringent than EU criteria, only because whenever we are around them or below them, we can be safe that the material meets the regulations and can be safely reused. So actually, for that reason, as I mentioned, our environmental agency has already a confidence of using this material in construction. Then here you have TCLP test, which only identifies if the material is hazardous or non-hazardous. And we meet the standard, which means that the slag, new sand, is a non-hazardous material. Here you have another test, typical behavior for leaching of different type of metals. Again, we meet the standards. I will not spend much time into discussion of those results. Following up with geotechnical properties, if you want to use this new sand as construction material, you need to meet geotechnical regulations that would tell you that it is actually similar to sand material. So throughout the accredited test, we identified that slag, as compared to river sand, is very similar and meets the same category for geotechnical tests, which means that it fits under fine aggregates. So whenever you do a construction, instead of using sand, you can use this material 100%. And have a confidence that structurally the concrete will be resistant. So this is how the new sand looks from different type of mixes that we use. And here a size distribution between the sand black line and that of the different mixes. So we are within a sand range. And so structurally, it's very similar. It's more maybe pointy. There is a little bit more needle-like structures, but those actually may have a positive influence in terms of sustaining the strength of the concrete, because it provides more surface area and better binding to different components of the concrete. Additionally, environmentally, analysis showed that quite often the sand that we import is has heavier contamination than this waste-derived new sand. Obviously, environmental contamination reason, depending where you collect the sand, you may expect higher heavy metal contents than in the material derived from waste. That's very surprising when we did that test. When you think about applying this material in construction, you must ensure that the strength of the concrete itself will be suitable for specific applications. So what we did, we created a mortar, basically OPC concrete, with cement, OPC cement with a new sand, 1-to-1 ratio. And we compared it between a sand and the different new sand coming from mixes of sludge and municipal solid waste. And you can see that the strength at different times of curing very much is similar for different type of mixes. Some need a bit longer in order to gain a final strength, but ultimately the strength of like what you see here would be very similar between sand and municipal solid waste and the sludge municipal solid waste mixes. We meet the criteria for non-structural concrete, and this is where we now are. We can construct whatever if this is a non-structural concrete. The next step in this research project will be to develop the mixes and test it for structural concrete. So again, here are more standards in terms of the concrete design that we have to follow and we meet. So ultimately, this type of material can be used in construction. So I hope you understand what I tried to convey. we recover energy, we still get a lot of energy from this type of waste. But aside of it, the residue does not need to go to the landfill, but can be used in construction. So ultimately, you create another vertical, another sideline into that circular economy concept without generating final waste material that has to be dealt with. So we have a confidence of treating sludge and municipal solid waste in this way, but sludge is still at 50% ratio. So currently, in the next generation project, we're going to look at feeding more sludge into the system, going to close to 100% treatment. Another thing is that, as I mentioned, waste to energy must be a vital part of the circular economy. And the only way is how we do it. I say, let's do it smart. Except of energy, let's recover the materials. With that, I leave you and I welcome any questions. Thank you.
Thanks very much, Greg. We're almost out of time, everyone. We'll take a couple of questions. I've got one here from Jun Park, just from the pictures at the end of my presentation. How does the Australian facility treat the emissions from the process? These are treated by basically standard processes of scrubbing and filtering the effluent gases. I take it that's what you mean, Jun. Would anyone else like to comment? Greg, Ron?
Yeah, I did mention in my presentation that part that actually almost like half of the line itself, the process itself, is to assure that the gas that is being released gonna be clean enough. So you need to follow regulations in a specific country. So for Singapore, our emissions are monitored online, and the information does not go to me as an owner of the facility, but they go directly to environmental agencies. So they see what is being released and at what quantity. Whenever we don't meet that standard, we would be notified. And obviously there are penalties, but the true mechanism behind this is to correct the process itself, so you don't release anything but to the environment. And you are correct, like lots of scrubbing of gases is being applied. You have to remove any acids that are in the process. So we use slackline and activated carbon in order to capture dioxins, heavy metals, and acidic vapor. So ultimately, whatever comes out of the stack is pure enough in terms of environmental assessment.
I believe that well, there are no facilities in Australia operating yet, but I believe that the parameters defining these stack gases will be available publicly for the general community to see. As far as you can get online monitoring, of course, you can't for dioxins and so forth. But this is the simple fact is we have extremely stringent regulations regarding the composition of the off gases, and these have to be met. Otherwise, the plants will be closed down. Are there any other?
Correct. I mean, you have to be really much open with everyone, what you are emitting and how the process operates.
Okay. We have to wrap it up, everyone. I've just been told, because we're running over time and there are other sessions. So please join me, everyone, in thanking Roni and Greg for their time. I think that was really interesting. I think energy recovery has got a role to play, as I said, and hopefully in Australia we'll see it occur sooner rather than later. Thank you very much, everyone. And thank you, Ali, for the opportunity to conduct this seminar. Thank you. Goodbye.